Hello, this is Mike Kolbeck, and I'd like to walk you through my implementation of Homework 1 for Neural Networks and Deep Learning at Depaul University. So up here you can see I've got my code here. This sort of panel over here is going to be my modification of the NN578 network code. And then over here are there's the scripts that are running that code and calling them in these network.network calls. So I'll walk you through the changes that I made and then show a couple of examples of this in action. I'll scoot this down just a little bit. So the first ask here is to reconfigure the evaluate function down here sort of towards the middle of the file. In the other versions, this would just return sort of an accuracy count, or a number of them that are correct. Now I am saving that here, but I'm also calculating an accuracy by dividing the total number of test results to check. And I'm grabbing a mean square error, an entropy value, and a log likelihood, and then I'm returning all of them in the form of this kind of array structure here. Now, where I got these from, the mean squared error and the entropy, you'll notice these might look kind of familiar. I took them almost writ large from the NN578 network 2, from the cross entropy cost and the quadratic cost objects, so these sort of functions you can see here. Then the log likelihood is just taken from the Book's formula, sort of the inverse of the log of x, and kind of summing all of those up. So once I have all those metrics for how that particular run or data point did, I return this in this array here, which is used further up in the application. So let's take a look at where this is used. So this evaluate is called by SGD, so this staircase of gradient descent. This is modified a little bit too. So what I've added here is this history list here that contains two sublists. The first one for the evaluations of the training data, the second one for the evaluations of the test data. If there is test data provided, it will go through and add them to that second function here by calling evaluate and adding them to history 1. And then regardless of whether there's test data for the training data, it will go through, test it out, and add it to history 0. So as it iterates through the epochs, it'll build these lists out kind of as a history of all of the runs and how well they did. And then once that's all done, we'll call this self.print history function, which I've added down here. Now this wasn't a specific ask, but this is something I wanted to do just to get a little more clarity on what's going on. So it just does sort of formatted printing down here to spit everything out in this format that you see down here. And then finally down in the backprop function, I added this activations.append zeros. So this is building the data structure of where the activations are going to go ahead of time, so that you're not taking this array and kind of dynamically resizing it every time you add activations to it. So this will just spit it out just containing zeros, and then when we actually save it down here, the activation, it'll override those zeros with the appropriate values. So just to kind of see this in action over here, I'm going to run this basic script just to kind of get an idea of what this looks like on some really basic data. We just have a couple of data points here and a very simple network. We can see that we're going to get the training and test output pretty much as listed on the homework assignment. In the second script here, I'm going to run this again and kind of confirm the way that this works over sort of a larger set. We can see it's running 30 epochs, and while we gave this a training set, it will give us all of the full history of that. But because we didn't give it any test data, we're just getting back these empty arrays here as requested. This third script is where it gets a little bit more interesting, and this is where we kind of can call the network in kind of like a real-like environment and get some accuracy values out of it, and kind of play with the network that we're using. So if I just comment this one out here, and I uncomment a different one, I can just try this and compare different neural network configurations with different numbers of nodes and different inputs to see what kind of accuracy we receive out of those. I was able to kind of fiddle with this a little bit, which you can see in my write-up. Got some pretty good accuracy counts, but I was never able to consistently hit this accuracy 1 here in the training set and kick out of the execution, which can be found up in SGD here. I was never quite able to get that consistent output from a configuration of the neural network. That said, my implementation here does support breaking out early. If you have any questions, hit me up at michael.b.kolbeck@gmail.com. Thank you.